Introduction to related rates. So many variables have a familiar relationship. In other words, a way variables are related to each other. An example of this is the Pythagorean theorem. A squared plus b squared is equal to c squared. Let's say a triangle's dimensions are changing. This means that a dimension has a rate of change, and this rate is related to another dimension's rate of change. For example, right? If we change one of the sides of a triangle, other sides of a triangle could be changing as well. Like that. You see anytime you change the side of a triangle, the other sides are related to it. So, if we have the rate of change in one side, calculus can help us figure out what the rate of change would be for the other sides. So this is actually going to be implicit differentiation here. So utilizing the Pythagorean theorem, you want to differentiate it with respect to time. Differentiate your relationship with respect to one specific variable. This is like implicit differentiation. Usually it's with respect to time, but not always. So we can implicitly differentiate this. We would get 2a dA dt plus 2b times dB dt equals to c dc dt. This is if you have, this is the relationship here. A is just how long A is, B is how long B is, C is how long C is, but dA dt is the rate of change of side A, dB dt is equal to the rate of change of side B, dC dt is equal to the rate of change of C. So sometimes you might not even have, like if I move it sideways, right? You see how side A doesn't change its length? Like the rate of change of side A is 0. So if this were the case, like dA dt would be 0, for example. But you see, if I move it diagonally like this, all sides of the triangle have some relation rate of change. So let's, in 4.4, we're just setting up equations. And then 4.5, you're going to work on, we're going to add some numbers to the problems to help you, so you'll be able to solve them. But we're focusing on the setup because that's the most important piece. So a police car approaching a right-angled intersection from the north. So you see right here, this is the right angled intersection. Draw that here. And the police car is right here approaching it from the north. So you see it's from here going down. It has turned the corner and is now moving straight east. So you see the speeding car is going towards the right. Set up a relationship, then find an equation that shows the related rates of the vehicles with respect to time. So you see as the police car is going down towards the intersection and the speeding car is going straight east, there is a right triangle set up like this. Oftentimes you're going to see right triangles, but it could involve other shapes too. So set up the relationship. So this is like an a squared plus b squared equals c squared. But let's just use variables because they give us an axis. Let's say x because this is the x-axis. Let's say this is y because it's the y-axis. And let's just say z for the diagonal. So x squared plus y squared is equal to z squared. And then you can differentiate it with respect to time. So 2x dx dt plus 2y dy dt is equal to 2z dz dt. This is just setting up the relationship, and then in 4.5 you'll likely see problems that have values that you can plug in and then solve for one of the variables here. So we're going to go over an example where some dimensions are constant. So an airplane, point A, is flying a horizontal path that will take it directly over an observer, point A. So see A is going to the right, so it's directly over, right here. It's flying on a horizontal path that will take it directly over an observer O. The plane maintains a constant altitude. So constant altitude, let's label these first. So x direction, because it's horizontal, y vertical, and then we can have this distance here be z. So the airplane maintains a constant altitude, so the y value never changes. So what we can say is dy dt is equal to 0, because the change in height or altitude, it doesn't change, it's just constant. Relate the rates of change of the distance between the observer and the airplane and the horizontal distance between the two. So we can still set, because this is the right triangle, we can still do x squared plus y squared is equal to z squared. And we can differentiate with respect to time again. 2x dxet plus 2y dy dt is equal to 2z dz dt. But here, remember, altitude is constant, so dy dt is 0. So this term right here is going to go to 0. We're going to remove it, and then what we're left with is 2x dx dt is equal to 2z dz dt. That's your answer there. You can go ahead and start the practice.